We discussed mainly last week, we discussed the strain tensor. So first of all, we discussed the current configuration. We said you have a configuration for some object, and this would be defined by the current configuration or the reference configuration. So this is basically a set of coordinates. This is the vector, and this is the components of this vector. And then we have a current configuration. So we have an original or a reference configuration, and then we have a current configuration. So this is x small, and these are the components. Sorry, this is not a vector. So this is a vector, this is the components of this vector. And then we define the displacement field. So the displacement field is basically x small minus x capital, and the displacement field is a vector. And then we said we have the gradient of the displacement vector, so that the gradient of the displacement vector is basically just the derivative of u1 with respect to x1, u1 with respect to x2, and u1 with respect to x3. We also have u2 with respect to x1, u2 with respect to x2, and u2 with respect to x3. And we finally have u3 with respect to x1, u3 with x2, and u3 with x3. So this is a tensor. I'm just going to write it such as a tensor. And then we have the strain tensor. So this is the E tensor, would be half the displacement gradient added to the transpose of the displacement gradient. Okay, so this is basically a vector, and this is a vector as well. Although this is a tensor. All right, so this is the strain tensor. Once we have the strain tensor, we said this is just a standard tensor. If you are interested in finding the change in the length in a certain direction, so for example, if you are interested in finding the change in the length in the direction n, then the change in the length, I'm going to call it ENN, is equal to n multiplied from left and multiplied from right. If we are interested in finding a change in the angle between two vectors n and m, then in this case, the change in the angle is twice this number, but you just find the shear strain. So this is n multiplied with E multiplied with m. So this is the change, or this is the shear strain. The change in the angle is basically twice this number. So this is half the, or this is half the change in the angle. You have to multiply it with 2 to get the change in the angle. This is the shear strain, and it expresses the change in the angle. And obviously we have the strain tensor. So this is the E tensor. You can find the principal strains, E1, E2, and E3. So this is the maximum change in the length in any specific direction. So we identify the directions by solving the eigenvalue problem, and then we get the eigen directions. So the eigenvalues are basically the change or the maximum change in any length in the direction of the eigenvector. And then we have the shear strain, and the shear strain, I mean, you probably can call it gamma max. So the maximum shear strain is just like we had for the stresses, is E1 minus E3, where we have these in order. So E1 is the largest, E2 is the second largest, and E3 is the smallest. So this is pretty much all the material we covered last week. So I've asked you to solve this example last week, and I'm going to show you the solution just now. So this is just an eigenvalue problem. We have solved enough eigenvalue problems. You just find the determinant and make the determinant equal to 0. We subtract lambda from the diagonal terms. You find the determinant, you make the determinant equal to 0. You find the values for lambda, and you get 6. So the principal strains are 6, 2, and 0. You put them in order. So this is the largest, so this is E1, this is E2, and this is E3. And these are the eigen directions, so this is the principal directions for the strain. And to find the maximum shear, you just subtract E1. You subtract E3 from E1, so it is 6 minus 0, so this is 6. Okay. The next part, or the last part of the presentation. So the last part is the compatibility of the strains. As we said before, for the stresses, we have an equilibrium that the stresses need to satisfy. It's similar for the strains. The strains are connected to the stresses, and they are basically connected to displacement. So if you look into the strains, you have 1, 2, 3, 4, 5, 6. So you have 6 independent components. Now, these 6 independent components are resulting from 3 independent stresses on. So in order, or 3 independent displacements. So for these components to be able to satisfy the condition that all of them would belong to only these 3 displacements, then we need to impose some extra conditions on them. And this is called the compatibility of the strains. So for any strain field or for any strain tensor to be able to check if it is computable or not, we need to check this set of equations. So basically, we have 6 equations, just similar to the number of the strains we have. And using these 6 equations, we can obtain unique 6 values for these 6 components. So the 6 equations, 6 unknowns, we can solve them and find unique values for the unknowns. Now, if you look into these equations, you'll see that all of them are second derivatives. So by default, if your strains are linear, then these equations are satisfied. I mean, if it is linear, you derive it the first time, you get a constant, you derive it the second time, you get a 0, and then 0 is going to be equal to 0 everywhere. Okay, so I'm going to do one example on this. And I will leave you some more examples in the tutorial. So we have 3 displacement components. So it is k x2 squared x1 and k 4x3 squared minus x2, and u3 is equal to 0. And we know that k is equal to 10 minus 3. So we need to find the strain tensor. So this is the first thing we are looking for. And then we want to find a change per unit length at a specific point and for a specific direction. So first of all, let us find the strain tensor. We have the displacements. I'm just going to copy the displacements over here. Oops. So the displacements are u1 is equal to k x2 squared minus 4 added to x1. And then we have u2, which is k 4x3 squared minus x2. I probably should be using capital here. And these are meant to be capital. So just rewrite them as capital answers. x2 and x1. And then for u3 is equal to 0. So to find the strain tensor, the first thing we need to do is to find the displacement gradient tensor. Which is basically this tensor here. So we need to find the displacement gradient tensor. So the displacement gradient tensor is the derivative of u1 with respect to x1, u1 with respect to x2, and u1 with respect to x3. So I'm just going to write this down. So this is the displacement gradient tensor, and this is a tensor. Okay, so the derivative of u1 with respect to x1, this is going to go to 0, and this is going to go to 1. And we have 1 multiplied with k. I'll just type k in here. So this is the first component. Now we look into u1, the derivative of u1 with respect to x2. So the derivative of u1 with respect to x2, so this one will go to 0, and this one will go to 2x2. The square will come down, and this will be left just as 2x2. We have k multiplied with that, so I'll just type it in there. It's 2kx2. And then the derivative of u1 with respect to x3, we don't have any x3 in there, so this is going to be 0. Now we come to the second row. The second row is the derivative of u2 with respect to x1 and x2 and x3. Just do the same procedure. So the derivative of u2 with respect to x1 is 0 because there is no dependence on x1. There is no x1 in there. So the derivative of this is going to be 0 and the derivative of this is going to be 0. So I'm just going to put 0 in there. The derivative of u2 with respect to x2 is going to go to -1. So this is -1. This guy is going to 0. So this is 0. And we have k multiplied with it. So it's just going to be -k. Going to write -k in there. And then the derivative of u2 with respect to x3. So this one is going to 0. And this one will end up as 8x3. All right, so the square will come down and multiplied with 4 is going to be 8. And we have the k to the outside. So it is going to be k 8x3. These, so I still have the u. So this is 8kx3. And then finally u3, the derivative of 0 with respect to anything is going to be 0, so we have zeros everywhere. Now this is the displacement gradient. We need to find also the transpose of the displacement gradient, so I'm just going to transpose that. So the transpose of u, this row would become a column, k, 2kx2, and 0. This row would become a column, so this is 0 minus k, 8kx3, and then this row would become a column, and this is only zeros everywhere. Now the strain tensor is basically the addition, as you can see here. This is the addition of the displacement gradient added to the transpose of the displacement gradient divided by 2. So I'm just going to add these two tensors together and divide the results by 2. So just add them together. I'll probably just try to fit the strain tensor here. So the strain tensor then would look like this. K added to k, I need to multiply with half here. So k added to k, this is 2k. 2kx added to 0, this is 2kx2. And 0 added to 0 is 0. Then I have 0 added to 2kx2. And minus k added to minus k, this is minus 2k. And then 8kx3 added to 0, this is 8kx3. And then 0 added to 0, this is 0. Shift it slightly downward. And then 8kx3, this is 8kx3. And finally 0 added to 0. I need to check that my strain tensor is symmetric, and this is symmetric. This is equal to this one is equal to this one, and this one is equal to this one. So this is symmetric. I'll just divide by half. I remove all the 2's, and the 8 will become 4. So it's just, and then I will take the k as a common factor. K is multiplied with basically every single term in here, so I'll just take the k as a common factor. So remove the 2's, and this will become 4. So this is basically 1 minus 1, and then I have k multiplied with everything, and this is 4. Okay, so this is the strain tensor. Do you have any questions on finding the strain tensor? Okay, so then let us continue this example. So the strain tensor is given here. I'm just going to switch back to the presentation. So the first step is to find the strain tensor. Then the second step is to evaluate the change in the length at a specific point and at a specific direction. So I'm going to copy this information over. So the specific point is we need to evaluate the strain tensor at the point 1, 2, and 1. And we need to find the change in length for the direction n. This is 1 over the square root of 2, 1, 1, 0 transpose. I'm just writing this as a row because it fits better. And then I'll add the transpose. So this is basically a column. All right. So the first thing is just to evaluate this. I mean, you can do it either way. So you just multiply with n from left and right and then substitute the points, or just substitute the points and then multiply with n from left and right. It works either way. I'm just going to start with this one. I'll just substitute the value in here. So at this specific point, the strain tensor is going to be, so I'm going to call it, what is the name of this point? It doesn't have any name, so I'm just going to call it point P. So at P, we have the strain tensor. 1 is constant, is not changing. X2, this is the value of X2. So I'm just going to replace X2 with the value of X2. So this is 2. 0 is not changing, it's staying as a 0. X2, again, is 2. And then minus 1 is a constant, is not going to change. And for X3, this is the value of X3. So this is the value of X3. I'm going to insert it in there. It is 4 multiplied with 1. So this is 4. I come to the third row. I have a 0 in there. And then for X3, again, X3 is 1. So it is going to be 4. And then I have a 0 there. So this is my strain tensor. This is my strain tensor at point P. I've got the value of the strain tensor, numerical value for that. And then I'm interested in finding the change in the length in this specific direction, which is n. So I just multiply with n from left and from right. So I'll just multiply it with n. Is 1 over square root of 2, 1, 1, 0. And 1 over square root of 2, 1, 1, 0. So you can multiply this one with the matrix first, or this one with the matrix first. I always start from this side, so I'm just going to do it from this side. First of all, I have 1 over square root of 2, 1 over square root of 2. This is a scalar. I'm just going to take it to the outside and make it 1 over 2. Now, this multiplied with this is 1 is going to result into a row matrix. So it's 1 multiplied with 1 added to 2 multiplied with 1. This is a 3. Of course, I have a 0. And then 2 multiplied with 1 added to minus 1. Then this is 1, because 4 multiplied with 0 is again a 0. And then finally, I have 0 multiplied with 1. 4 multiplied with 1, this is 4. And then 0 multiplied with 0. So this is 0 except for 4 multiplied with 1. Now I have 3, 1, 4 multiplied with 1, 1, 0. This is 1 multiplied with a 3. This is, I have the half outside. 1 multiplied with 3, this is a 3. Added to 1 multiplied with 1, this is 1. Added to 0 multiplied with 4, this is 4. So it is basically half multiplied with 4. And this is going to be 2. So the change in the unit length at this point and for this specific direction is 2. Now I forgot to add the k. I have it there. So this is the k. And then it's basically just a constant multiplied with the whole thing. So this is basically the k. I'll just keep it in there. And it is staying here and staying here. So it's basically the change in the unit length is 2k. And I know k is 10 to the power minus 3. So it says here k is 10 to the power minus 3. So I have the change in the unit length is 10 to the power minus 3. So this is En. Well, the last part, are the strain components computable? So we go to the strain components. So this is the strain components, and we need to check their compatibility. So it is 1, x2, 0, and these are the entries. These are the components of the strain tensor. So I'm just going to go to the strain compatibility conditions. Let us move to this set of equations. So the first equation is the derivative of E11 with respect to x2 twice, derivative of E22 with respect to x1 twice, and the derivative of E12 with respect to x1 and with respect to x2 multiplied with 2. I'm just going to copy this set of equations, probably easier than moving backward and forward. I'll just put them here. Okay. Okay, so the derivative of E11 with respect to x2 twice. E11 is a constant. The derivative of a constant with respect to x2, this is going to be 0. And then we have the derivative of E22 with respect to x1 twice. E22 is a function of x2, and the derivative of a function, the derivative of E22. Sorry, this is E22. So E11, E22. And this is again a constant, the derivative of a constant with respect to x2, this is 0. And then finally, we have E12 with respect to x1 and with respect to x2. You derive them in any order you want. The derivative of E22 with respect to x2, this is x2 with respect to x2 is equal to 1. And then the derivative of constant with respect to x1 is a 0. So 0 plus 0 is equal to 0. So the first equation is satisfied. We can check now. So this is satisfied. The second set of equation, the derivative of E22 with respect to x3. So E22 is a constant. The derivative of that with respect to x3 is 0. And then we have E33 with respect to x2. E33 is a 0. The derivative of that with respect to 0 is again a 0. And then we have E23. So this is E23 or E32. So these two components are the same. So E23 with respect to x2 and with respect to x3. The derivative of this with respect to x3 is 4, and then the derivative of that with respect to x2 is 0, or you can do it the other way around. The derivative of this with respect to x2 is 0, and the derivative of 0 with respect to x3 is 0. So you'll always get 0 at the end. So this is equal to 0, and you can repeat the same thing for all the remaining equations. So this is satisfied. And you can repeat the same thing for all the equations. You will see that you always get 0 equal to 0, because as I said, if you look into the exponent, if you look into this exponent there, you'll see that these are second derivatives. So this is derived twice in all the cases. In all the terms, every single term in here is derived twice. And because it is derived twice, and you have linear functions in your case, in this case, you only have linear function, then in this case, is going to be 0 is equal to 0. So this one is also differentiated twice, one with respect to x1 and the second time with respect to x1. This one is derived with respect to x2 and x1, and this is x3 and x1. So this is all differentiated twice for all the entries in these equations. And since you have linear functions in there, I don't see any squares or cubes in there. This is only constant and linear functions of x2 and x3. Because of that, you will have these compatibility equations satisfied anyway.